Hi, my name is Yunfeng Zhang, and I will present our paper Debiasing Bias Measurement. This is a joint work with my colleagues Dr. Kristian and Dr. Amanda Bauer. We're all from the Twitter Meta team, where Meta stands for Machine Learning Ethics, Transparency, and Accountability. Let us start with a hypothetical scenario. Suppose that we created 3 different machine learning models for classifying toxic comments, and we measured their accuracy over 40 different languages. We then plot the accuracy data in a graph like this. The height of each bar represents each model's accuracy on the language. Now consider this question. Which model has the lowest group-wise performance disparity? In other words, which model performs most consistently over all languages? Note that this group-wise performance disparity is what we often refer to as model bias in the AI fairness field. When the number of groups involved is this large, you may find the question we posed difficult to answer. You can see that the visualizations are very helpful here, and also canonical bias metrics such as statistical parity difference and predictive parity difference don't work here because they only measure differences or ratios between 2 groups. What we need are well-designed summary metrics that work for large numbers of groups. We call these metrics MetaMetrics. We have identified several MetaMetrics from the academic literature and open source tools. They can be roughly divided into 2 categories. One category reports the extreme disparity among groups, and the other focuses on some kind of average deviation between the model performance on each group and the average group-wise model performance. In this research, we will focus on the variance metametric that hasn't received much attention in the field. We will show later that it has some nice mathematical properties that make it, in some sense, a better metric than others. So these are the metametrics that we found in use today, and they're included in some open source libraries. But are they reliable measurements? Are they statistically unbiased? To answer these questions, we ran a set of Monte Carlo simulations. Unfortunately, we found that all of the above-mentioned metametrics are statistically biased, and they all overestimate the true group-wise performance disparity. Here's how we set up the simulations. In each simulation experiment, we generate performance metrics yk for each group k using binomial distributions. The parameter of the binomial distribution, mu k, is the true performance metric of group k, and yk is an estimator of this true performance metric. These mu k's are said to be equally spaced between a variable lower bound L and then a fixed upper bound 0.9. And so a smaller lower bound L leads to more uneven group performance. After getting a sample of the group performance metrics, we can then calculate metametrics over yks and mu k's, which are represented by my and mu. Finally, we average metametrics over 1,000 simulations. The difference between the average my and the average mu is the statistical bias. The result of the simulation is plotted here. The y-axis shows the statistical bias, and the x-axis shows the number of groups. As you can see, the biases are all positive no matter which metametrics we use, and as the number of groups increases, the bias also increased. We can even prove mathematically that some metametrics have upward statistical bias. Here's the proof for the mean absolute deviation metametric. I won't go into the details, but we can also prove it for max absolute deviation and variance metametrics using similar derivations. There is also an intuitive way to think about the bias. Suppose we have several groups that have the exact same true performance metrics, so same mu's. The between group variance in this case would be 0 over the mu case, but the sample performance metrics would not all be the same because of sampling noise. And so the variance over these y's would have to be larger than 0. From this reasoning process, you can see that the statistical bias of my is introduced by sampling noise. So this also explains why as the number of groups increases, the bias increases, because larger number of groups means smaller group size when we keep the total number of instances constant, which in turn means larger sampling noise. Of course, in general, we want metrics to be as unbiased as possible, but there are also practical reasons why this overestimation of group-wise performance disparity is problematic. One, it may mislead policymakers to make unnecessary adjustments to a model. And because there are often fairness accuracy trade-off, model developers may sacrifice more accuracy than necessary in order to reduce group-wise performance disparity, resulting in a less performant model for all individuals. And two, biased metametrics means that they cannot be compared across different grouping methods. For example, consider a case where we have two different ways to group people by age for the same dataset, and maybe one uses larger buckets than the other. And the metametrics calculated across these two different age grouping methods are not directly comparable because they don't have the same amount of statistical bias. Therefore, this hinders us from making fair model comparison. We therefore set out to find ways to correct for this overestimation bias. Through mathematical derivation, we found that for the variance metametric, we can get an analytical expression for the bias, and therefore remove it entirely. This first equation here shows how to get an unbiased estimate of the variance metametric. We're basically subtracting from the biased variance estimate the average sampling variance across groups. The larger the sampling variance, the larger the statistical bias. As it turns out, this equation has been discovered before in other contexts. It was first introduced in 1950s and then popularized by Hedge and Oken for meta-analysis in the 80s. In these other contexts, this second equation, the truncated version, is used more often, and it's used to preclude the possibility of negative variance estimates. And we adopt this convention for the remainder of our study. Now, to test this correction method, we again ran some simulations with two factors, equal group size versus unequal group size, and equal performance versus unequal performance. In the equal group size conditions, all groups have 50 instances, and there are 100 groups. In the unequal group size conditions, the group size ranged from 10 to 90. In the equal performance condition, the performance metric mu k is always set to 0.8, so the true variance is 0. In the unequal performance condition, mu k ranges from 0.1 to 0.9, and the true variance is 0.055. We ran the simulations as before and generated YKs, which are the performance metrics for each group. The only difference now is that to apply the correction, we also need to calculate the sampling variance of YK. Because we're using binomial distributions to generate YK, we can directly use the plugin estimator shown on the right here for sampling variance. So we plot the distribution of the variance estimates for all simulations as histograms. Each panel here shows a different condition. The black vertical lines show the true variance. As you can see, the uncorrected variance estimates, these red histograms, are still showing upward bias, but the distribution of the corrected estimates, the green ones, are all centered at the true variance. Therefore, the correction is working. Now that we have an unbiased point estimate of between group performance variance, it would be useful to also work out the uncertainty interval for this estimate. Such uncertainty intervals will help us draw conclusions about the statistical significance of estimates. For example, if a 95% uncertainty interval doesn't include 0, we might conclude that the model's bias as measured by group-wise performance variance is statistically significant. We can estimate uncertainty intervals through bootstrapping. First, we run our original generative model, the first equation here, to get one row of YKs, which are the observed performance metric per group. Then we resample the observations within groups to get the bootstrapped YK stars. We do this 500 times to get 500 different bootstrap samples. Then we calculate the uncorrected and corrected variance estimates. So here, each of the histograms consists of estimates from the 500 bootstrap samples. We can then determine the 95% uncertainty intervals by calculating the lower bound at the 0.025 quantile and the upper bound at the 0.975 quantile of the samples. These uncertainty intervals are plotted as horizontal error bars here. Unsurprisingly, the uncertainty intervals for uncorrected variance estimates do not cover the true between group performance variances. But what's puzzling to us was that even the uncertainty intervals for corrected variance estimates are also shifted upwards, and they also do not cover the true values. So what is going on? Well, it turns out bootstrapping induces its own variance. We have only corrected for this part of statistical bias by using our correction method, but if we use bootstrapping, we need to also correct for this part. So as a result, the equation for sampling variance of bootstrapped YK is the one at the bottom, not the plugin estimator anymore. After applying double correction to the variance estimates, our 95% bootstrap uncertainty intervals now cover the true between group performance variance, which can be seen here as the blue error bars cover the black vertical lines. We further validated the method over 1,000 replicated simulations, and as you can see, indeed the double corrected uncertainty intervals cover the true values at least 93% of the time. So great, now that we have an unbiased between group performance variance estimator, let's test it on some real dataset. We applied it to the adult income dataset. For those who are not familiar with it, it contains demographic and work information of over 48,000 individuals from the 1994 census database. There are a total of 14 features, and the task is to predict whether an individual's annual income was above $50,000. We split the data into 70% training and 30% test datasets. We trained a gradient-boosted tree classifier, which has an overall accuracy of 87%. For our purpose, we are interested in how the model performs on different age groups and races. We also tested our method on 3 different performance metrics: false positive rates, true positive rates, and selection rates. These bar graphs show the performance measures across different groups. As you can see, there is a considerable variability in these performance metrics. We obtained the 95% uncertainty intervals for the between group performance variance estimates using both the standard uncorrected method and our double correction method. As you can see, in some cases, like for the true positive rate matrix, the double corrected uncertainty intervals overlap with 0, but the standard uncertainty intervals do not cover 0. In other words, had we used the standard methods, we could have mistakenly concluded that there are large statistically significant between group disparities, and we might perform unnecessary model changes that could result in worse model performance for everyone. To conclude, we have identified a new type of metrics called MetaMetrics for measuring group-wise model performance disparities, particularly for large numbers of groups. We showed that these MetaMetrics are statistically biased measurements, but we developed an unbiased estimator for between group variance. We also developed a double corrected estimator for quantifying the uncertainty of between group variance. For future work, we hope to examine other methods for measuring between group variability, particularly those from the meta-analysis literature. And we also would like to investigate corrections for other metametrics such as max-mean difference. And last but not least, we want to caution that MetaMetrics cannot capture the entirety of the impact of ML systems. Small measured disparities should not be taken as a guarantee that the system is fair or free from adverse impact. And that is all I have. Thank you.